breakthrough in extreme electromagnetic fields, shrinking particle colliders to a chip. Imagine harnessing extremely powerful electromagnetic fields right inside a laboratory. An achievement that could redefine the boundaries of scientific research as we know them. But here's where it gets controversial. Traditionally, producing such formidable fields demands enormous and costly facilities, like the Large Hadron Collider at CERN, stretching miles across the landscape and costing billions. What if you could do the same on a scale that fits on a chip? That's exactly the breakthrough Assistant Professor Aakash Sahai from the University of Colorado Denver has pioneered, opening doors to new physics, chemistry, and medical explorations previously thought impossible without massive infrastructures. Sahai's motivation is rooted in a pressing concern. Our entire scientific community faces a bottleneck because cutting-edge experiments require facilities so large and expensive that only a handful of exclusive groups worldwide can access them. Current technologies rely on accelerators that span tens of miles, demanding enormous investments, Sahai explains. This exclusivity risks stalling the future of scientific discovery for upcoming generations. So how did Sahai tackle this challenge? His approach fuses three fundamental elements: specially designed materials, quantum gases, and lasers. Over decades, accelerator science has treated materials involved in these experiments as disposable or single-use due to their inability to withstand high-intensity beams. Contrarily, Sahai's materials exhibit extraordinary resilience, owing to unique heat transport mechanisms governed by quantum physics, allowing these materials to survive intense particle collisions without deteriorating. At the heart of this innovation lies the concept of a quantum electron gas. Unlike classical particles, electrons in conductive materials occupy distinct quantum states, creating a collective termed a quantum gas. Sahai's groundbreaking work is the first to deeply analyze how this quantum gas can be excited in an extreme, nonperturbative manner, producing what he calls extreme plasmons. These extreme plasmons, once activated by particle beams, generate highly focused electromagnetic fields. What's remarkable is that the oscillations occur at such incredibly short wavelengths that they cause particles to emit coherent gamma-ray photons, a phenomenon reminiscent of X-ray free electron lasers found in advanced facilities like the LINAC Coherent Light Source, LCLS. Now, picture a tiny cube of conductive material, just a micrometer across, containing billions of electrons vibrating in a confined space. When excited, these electrons compress dramatically, generating intense electromagnetic energy that manifests as a powerful electric field. According to classical physics principles, particularly Gauss's law, a dense charge leads directly to a strong electric field. Sustaining these intense fields without the material falling apart was a major hurdle. Sahai's team overcame this by leveraging a fascinating quantum effect called relativistic ballistic transport, which allows heat to dissipate efficiently without collisions that would damage the material's structure. This ability to manage heat flow while preserving the integrity of the material under extreme conditions could ultimately enable scaling down massive particle colliders to chip-sized devices. As Sahai's graduate student, Kalyan Tiromalasetti, puts it, the true breakthrough is controlling such high-energy interactions without destroying the very fabric of the material. It's like taming a wild storm inside a delicate crystal structure. Looking ahead, these extreme electromagnetic fields offer powerful potential for fundamental physics research. Sahai outlines three major long-term goals: developing a new class of particle accelerators using extreme plasmons to investigate mysteries like dark matter and dark energy, achieving nanostructuring of ultra-intense electron beams to generate coherent gamma rays, and focusing these beams so precisely that they could explore phenomena such as vacuum polarization. One intriguing future application was the possibility to experimentally test predictions from string theory, a highly theoretical framework that has eluded empirical validation so far, by pushing the accessible electromagnetic field strengths even higher. What's truly surprising, and perhaps sparks debate, is how skeptics in the international accelerator physics community initially dismissed this approach as purely theoretical. Sahai shares, when early experimental evidence started supporting our predictions, the excitement was beyond description, especially considering the skepticism we faced from well-established experts around the world. Nevertheless, challenges remain. The prototype materials currently used are akin to the earliest rudimentary transistors or microchips made decades ago, far from optimized. Sahai emphasizes that off-the-shelf elements don't offer the precision needed. Instead, custom-engineered materials with finely tuned structural and microscopic properties are essential to unlock the full potential of this technology. The team is actively seeking funding to enhance the plasmonic chip's design and fine-tune its capabilities. Their ongoing experiments, part of the E339 effort at SLAC National Accelerator Laboratory, focus on decoding subtle details in experimental data to broaden accessible parameters and deepen understanding of the underlying quantum physics, territory that has largely remained unexplored until now. Sahai hopes that by securing further support, they can produce high-quality quantum materials and derive fundamental scaling laws. These advances promise not only to propel future scientific research, but to transform how we explore the universe at its most fundamental levels. So what do you think? Is it feasible to miniaturize colossal particle accelerators onto tiny chips, revolutionizing how science is done? Or are the challenges too great, with risks of oversimplifying complex quantum phenomena? This debate opens up fascinating questions about the future direction of physics research. We'd love to hear your thoughts. Agree or disagree, share your perspective in the comments below. Revolutionary breakthrough, shrinking particle accelerators onto a silicon chip. Revolutionary quantum discovery could transform particle accelerators into chip-sized marvels. The scientific community is on the verge of a transformative breakthrough as researchers harness the extraordinary potential of tiny entities called plasmons. These microscopic phenomena enable scientists to concentrate immense electromagnetic energy within spaces tinier than a sand grain. A recent scientific advancement involving these particles could completely transform multiple fields, ranging from fundamental physics to advanced medical treatments. The extraordinary world of extreme plasmons. At the core of this scientific leap are what experts call extreme plasmons. These differ dramatically from conventional plasmons. While standard plasmons involve subtle, minor electron oscillations, extreme plasmons create powerful, intense vibrations. These oscillations approach the very physical boundaries of how electrons can move. The result? These vigorous movements generate electromagnetic fields of staggering power, reaching the petavolt per meter (PV meter) range, which vastly exceeds anything scientists have previously created in laboratory environments. But here's where it gets interesting. Until this breakthrough, researchers struggled to effectively manage these powerful plasmons. That changed when Assistant Professor Aakash Sahai from the University of Colorado, Denver, developed a method to control them in a reliable and secure manner. Sahai and his research team created an innovative quantum kinetic model that accurately describes extreme plasmon behavior at nanoscales. Their groundbreaking research, published prominently in Advanced Quantum Technologies, could revolutionize experimental physics as we know it. This development is tremendously exciting because it will create entirely new research domains and deliver tangible real-world impact, explained Sahai. Throughout history, we've witnessed technological innovations that propelled humanity forward, like some atomic structure discoveries leading to lasers, computer processors, and LED technology. This breakthrough, which also stems from materials science, follows that same transformative trajectory. The mechanics, creating extreme fields on microscopic chips. Currently, researchers studying powerful electromagnetic fields require enormous, expensive particle accelerators. Facilities such as CERN's Large Hadron Collider extend nearly 17 miles beneath the Earth's surface, accelerating particles to near-light speeds to detect fundamental particles or investigate elusive dark matter. Astonishingly, Sahai's innovation could potentially compress these massive machines onto silicon chips smaller than your thumbnail. Is the multiverse real? How new quantum tech could prove it and cure cancer. Is the multiverse a reality? New quantum technology could provide answers. Imagine a groundbreaking gamma-ray laser that can effectively target and eliminate cancer cells while leaving surrounding healthy tissue completely unharmed. An engineer from the University of Colorado, Denver, is on the verge of equipping researchers with a revolutionary tool that could bridge the gap between science fiction and reality. Picture the immense potential of a gamma-ray laser that can accurately destroy cancer cells without affecting the nearby healthy cells. Alternatively, envision a device that can delve into the very structure of the universe, testing theories such as Stephen Hawking's intriguing concept of the multiverse. Assistant Professor Aakash Sahai, Ph.D., from the Department of Electrical Engineering, has achieved a significant breakthrough at the quantum level that could pave the way for these exciting possibilities. His discovery has sparked considerable interest within the quantum science community due to its potential to revolutionize the fields of physics, chemistry, and medicine. Notably, his work was featured on the cover of the June issue of Advanced Quantum Technologies, a prestigious journal dedicated to quantum materials and research. This is incredibly thrilling because this technology will unlock entirely new areas of study and have a tangible impact on the world. Sahai expressed, "Historically, we have experienced technological advancements that have propelled us forward, such as the understanding of subatomic structures leading to the development of lasers, computer chips, and LEDs. This innovation, rooted in material science, follows a similar trajectory." Understanding the mechanism. Sahai has developed a technique for generating These fields are produced by the rapid oscillation and scattering of electrons within materials and are crucial for technologies ranging from microprocessors to the powerful particle accelerators used in the quest for dark matter. Traditionally, creating such strong fields has necessitated large, complex infrastructures. For example, the Large Hadron Collider at CERN in Switzerland stretches over 16.7 miles and employs advanced radio frequency systems and superconducting magnets to accelerate high-energy beams. Operating facilities of this magnitude requires substantial funding, extensive infrastructure, and carries inherent technical risks. To address these challenges, Sahai has engineered a silicon-based, chip-scale material capable of withstanding the impact of high-energy particle beams. This innovative material effectively channels the energy generated by the oscillating quantum electron gas while maintaining structural integrity by managing the heat produced. The swift motion of electrons is what creates the electromagnetic fields. Sahai's breakthrough enables researchers to study high-energy field behavior within a device no larger than a thumb, potentially leading to a reduction in the size of massive accelerators to a compact, chip-based format. The ability to manipulate such high-energy flow while preserving the material's structural integrity is the real breakthrough, stated Kalyan Tirumalaisetti, a graduate student in Sahai's lab who is actively involved in the project. This technological advancement has the potential to create a significant positive change in the world. It revolves around understanding the principles of nature and leveraging that knowledge to make a beneficial impact. The technology and methodology were developed at CU Denver and tested at the SLAC National Accelerator Laboratory. a premier facility operated by Stanford University and funded by the U.S. Department of Energy. Potential applications of this technology. CU Denver has already filed for and received provisional patents for this technology, both in the U.S. and internationally. While practical applications may still be years away, the prospect of gaining a deeper understanding of the universe and improving lives is what drives Sahai and Tirumala to dedicate long hours in the lab and at Slack. Gamma-ray lasers could soon become a reality, Sahai remarked. We could achieve imaging of tissues, not just down to the nucleus of cells, but even to the nucleus of the underlying atoms. This means that scientists and medical professionals would be able to observe processes at the nuclear level, potentially accelerating our comprehension of the immense forces that operate at such small scales, while also leading to enhanced medical treatments and cures. Ultimately, we could develop gamma-ray lasers capable of modifying the nucleus to eliminate cancer cells at the nanoscale. The extreme plasmon technique could also facilitate the testing of a wide array of theories regarding the workings of our universe, from the possibility of a multiverse to probing the very fabric of our reality. These exciting prospects resonate with Tirumala, who once contemplated a career in physics. Exploring nature and understanding how it operates at its fundamental level is incredibly important to me, he shared. However, engineers provide scientists with the tools to do more than just comprehend, and that's exhilarating. Looking ahead, the duo plans to return to SLAC next summer to continue refining the silicon chip material and laser technique. Unlike the rapid advancements depicted in movies, developing groundbreaking technology can take decades. In fact, some of the foundational research that led to this pivotal moment began in 2018, when Sahai published his initial findings on antimatter accelerators. It's going to take time, but I believe it is very likely to happen within my lifetime, Sahai concluded. Reference: Extreme Plasmons by Aakash Sahai, 19th May 2025, Advanced Quantum Technologies, DOI 10.1002 QTE 2025-0037. Stay updated on groundbreaking discoveries. Subscribe to the SciTech Daily newsletter.